I'm going to talk today about some work we did recently on anti-distillation sampling. And to motivate this is actually a fairly well-contained problem and one that I think is pretty interesting. But the basic question is the following. Can we release a model, a closed source, sort of query-only black box model, where you can generate samples from this model, but training on those samples does not improve a student model? Okay, now there are obvious competitive implications for doing this, right? I think companies want to release closed source models without being able to sort of have open source variants that are as good as them. But I think there are also some real safety implications too. I do think there's value in at least a period of having closed source models that are at the frontier ahead of open source models to understand what their capabilities are. And I would rather not live in a world where every time a closed source model is released, we can easily clone it with an open source variant, right? That's my personal belief. And beyond that, I just think it'd be interesting to think about, can you create samples that somehow aren't very useful for training on? And that's the goal of anti-distillation sampling. So here's the setting. We have a teacher model. And we can draw samples from the teacher model. The teacher model specifies some distribution over next tokens given previous tokens. And we can sample according to it. And all you can get actually as a third party is just samples from this model. We also have a student model, but we actually don't know quite what student we're going to actually, someone downstream might be using. And so we're going to think of it actually as a proxy model. We're going to have some proxy student model. And we're going to think of this model as being trained on the samples from the teacher. So whenever we take a sample from the teacher model, xt plus 1, we would then actually take a small gradient step on that token in the proxy model. So that's how we update these proxy model parameters. And then finally, we have some downstream loss, L, which is a function of our proxy model. And this measures kind of how good the proxy model actually is, right? So it measures kind of how good it is on some, in this case, kind of differentiable downstream task, like maybe how good its likelihood is in a large corpus of data that we think kind of corresponds to something like the task at hand. Now, what we want to do, and the goal of anti-distillation sampling, is really quite simple. We want to sample from the teacher model, but do it in a way that mixes together two different objectives. On the one hand, you want to sample terms that have a high likelihood under the teacher model, right? So that's the first term. That's just normal temperature-based sampling, as you would normally have when you're sampling kind of any LLM. And the second term is the interesting one here. It trades off between, again, tokens that are likely under the teacher model with tokens that cause the loss of this proxy model to actually increase when you train on that one token. Okay, so just again, going back to the notation here, theta plus p is the updated proxy model. We want the loss of the updated model to be larger than the loss of the original model, right? You try to minimize the loss normally, so we want the loss to be larger. And so we want this difference here to actually be positive. And therefore, we're going to sample tokens that tend to favor increases in loss for the proxy model. Now, I just want to make the point here that doing this naively is not really practical. This loss L is pretty complex to actually evaluate. It takes some time. Think of it as the loss of the student model on some very large corpus. And that loss depends on the token you sample. So in theory, you would have to sort of evaluate this loss for every possible next token every time you want to generate a single sample from your model on some large downstream corpus. And I don't have the time to sort of go through it. This is the kind of the fun math part of this paper. But it turns out that using some kind of clever tricks that coming from basically just differentiation, they're not that clever, but they were fun to work on. It turns out you can actually evaluate that thing efficiently for all possible next tokens. So for all possible sampling points, you can find the next sample that maximizes that trade-off using just one forward pass, like you would normally have to in the teacher model, and 2 forward passes in the proxy model. All right, so I won't go over this. It basically involves just the directional derivatives and finite difference approximations done in 2 different ways, which lets you do this efficiently. Okay, so that's the approach. That's actually all I'll have here. I'll have to defer it to the paper for the actual details, but it's relatively cheap to actually compute this. And so the question is, does it work? And the answer is sort of kind of. I need to make the big point here. This is not really a practical approach yet by any means, but I think it is interesting how well it can do already. So the blue line here shows the trade-off you get between student accuracy on some downstream tasks. This is the GSM 8K kind of simple math questions. This shows the trade-off between student accuracy or teacher accuracy when you sample according to different mechanisms, and student accuracy when you train on the generated samples. And so what we see here is if you just use temperature scaling to generate noisier samples, those samples are still very helpful for the student model to train on, right? So, increasing the noise to the point where the teacher gets, 50% accuracy still provides pretty useful samples. Whereas when you sample with this alternative approach, again, you're still paying a relatively large hit here in teacher accuracy. This is not really something you'd want to do. But I think it's quite interesting that, for a relatively small change in teacher accuracy, you can actually make the student perform no better than the original student baseline did. So this is essentially with 70%, the drop of a third or a quarter or so in teacher accuracy, you can get samples that do not help the student at all. Right? And that's kind of interesting because you're still doing quite a bit better. You're still solving the problems as far as the teacher's concerned, but your generated samples are actually kind of not very useful. So it's also kind of instructive to look at what these samples look like. I won't go over it too much here. These are samples generated at the 80% accuracy level for the teacher. So this is sort of right around here. So this sort of, decreases the value of the samples from 62% of student accuracy to about 45%. And in doing so, it's really interesting because the traces, they're mostly reasonable, but you get funny things like XML RPC codes when talking about, middle school students and money problems in middle school students. So what you kind of get are mostly good-looking traces with a few kind of adversarial examples thrown in there, kind of naturally out of this process that degrades student performance when you train on it. Now, I'm sure you can circumvent this, by the way, if you want to sort of write filters after the fact, you want to try to sort of sample it after the fact. But if you do something naive, it doesn't. It in fact degrades student performance quite substantially, sometimes in ways that are a little bit obvious, but sometimes in ways that are really subtle that you can't quite see. It just somehow changes the samples to be not very useful. To sort of conclude with, I don't think this is something you want to do yet, right? It involves 2 more forward passes, even in a smaller proxy model to generate samples from your model. But I think it's sort of conceptually very interesting that we can actually start to generate samples that target some secondary objective when they are used to train a student model from those samples. And the very interesting thing is that this can actually be computed efficiently whenever your downstream loss sort of involves the difference of the difference of losses between the updated and the non-updated proxy model. So anyway, more information is available here. I think it's more an interesting kind of project at this point, an initial sort of exploration rather than something you'd actually want to use in practice. But nonetheless, I find it kind of cool that it's possible to in fact generate samples that have this property, to have a very different kind of trade-off in terms of how useful they are for training. All right, thanks very much.